Now let's talk about electric fields. Electric fields are fascinating and they really help us discuss and discover what happens around both static and moving charges. But for this unit, we're going to kind of focus on the static charges. Now, Michael Faraday was a British scientist and he came up with some fascinating ideas that maybe electric charges were affected by forces that occur over a distance. And so we attribute a lot of our theory of fields to him. Now, there are some characteristics of electric fields that you need to know. All right. The electric field fills the space around every electric charge. So if I have, say, a positive charge here, the electric field fills this entire space. Now I'm going to draw the field lines. We're going to discuss what this means in a bit. And actually, that's kind of a crummy field there. But it fills the entire space. So while we're going to draw it with arrows, another way to draw it, if this is my positive charge, is instead with different intensities. And here my intensities are actually going kind of cattywampus and backwards. All right, but each circle represents a different intensity. But the whole point is it fills the entire space. Now, the force that one electric charge exerts on another is really an interaction between their fields. So there is no direct contact between the charges. As a matter of fact, we pretty much never talk about two charges touching each other. And electric fields are vectors. So if I have an electric field at this point going to the left, and we're going to call that E1, E is for electric field, and E2 is going up. Are you feeling vector addition? Break things into X and Y components. Add the X components, add the Y components. The resultant is going to be the square root of EX squared or E1 squared plus E2 squared. So, my pre-AP kiddos, you're going to have to be able to do this. My grade level kids, we're going to do it more like this, E1 and E2. You have to add them like vectors. Now, the magnitude, remember the magnitude just means it's the actual number. It's the electric field strength. All right, is measured by its effect on a charge located within the field. Now, there may or may not be a charge sitting in my electric field. This is physics. We live in a happy physics world. So in my happy physics world, I am going to create a test charge. And my test charge is what I'm going to pretend magically place in my magnetic field, or excuse me, in my electric field. Now my test charge has certain characteristics. It's got to be small. We're going to pretend like I have taken a tiny little charge and I put it in this field, and the charge itself is so small it doesn't affect the field itself, but I'm going to measure what happens to that charge. Now, wherever the force acting on my tiny little test charge is large, tells me I have a strong field. Wherever it's weak or small, tells me I have a weak field. That kind of makes sense. A strong person is going to exert a strong force, and a weak person is going to exert a small force. Now, electric fields are always measured in newtons per coulomb. We're not being real creative with this one. Let's look at the direction of the electric field. Now, this is always the definition. The direction of an electric field is a direction it would push a positive test charge. Remember, spit on the person in front of you. So just take a tiny little positive charge. Now, if this is positive, what direction is it going to push my tiny little positive test charge? Well, it's going to push it away from the center along this line. What if I put a tiny test charge on this position? But due to a positive test charge, it's going to push it this way. So you see we wind up with this, what's called a radial field. Now, if a particle is positive, it's going to be pushed away from the particle, because if you have a positive charge, of course, that is going to push it away. However, if the particle producing the field is negative, it's going to suck it in, because a negative charge is going to be attracted to your, a positive charge will be attracted to your negative charge. So if I put a positive test charge, it's going to bring it into the center. So at every point, and I'm only doing representative points because it's too much to do them all. All right. Now, the formula is quite straightforward. The force acting in a uniform electric field, and I please want you to pay attention. I'm going to give you, there are different formulas we're going to use here, and it's very important that you know when we're using them. This is the force acting on a charge in a uniform field. Now it turns out we create uniform fields by parallel plates where one is positive and one is negative. Don't worry about that. Okay, we're going to get into capacitors later. But let's take my positive charge here. And this is my positive test charge. Now what's going to happen to my positive test charge if I put it near a positive plate? It's going to be pushed away. So my electric field is going to go from my positive plate to my negative plate. Now, if my charge is of a charge Q, then we are going to measure Q in coulombs. And my uniform field is newtons per coulomb, or N per C. Now my force is always newtons. So F equals QE. Essential formula that you need to know. But you see kind of how straightforward it is? The force, let's think about this. The force is equal to the charge, the magnitude of the charge, times the strength of the electric field that it's in. Think about your weight. All right? Your weight, let's change ink color here. Your weight, oh, lost it. Fg is equal to your mass times the strength of the gravitational field you're in. Do you see the correlation there? Now, what if we have an electric field due to a point charge? This is very different from a uniform field. If it's due to a point charge, it changes. Here you see that E is kQ over d squared, where E is your electric field, K is Coulomb's constant, or 9 times 10 to the 9th Newton meter squared per Coulomb squared. Q is a charge causing the field. That's this center thing in the middle. It is not your positive test charge. It's the charge causing the field. And D is, of course, the distance you are from, oh, I guess it's up here. D is the distance you are from the charge. Okay, that distance right there. Do you see now we have a 1 over r squared relationship? It's directly proportional to the charge. So a stronger charge will cause you to have a stronger electric field. But the further you get from that charge, the smaller the field is. Now, I've been drawing electric field lines, but I haven't been explaining them. Let's go over some rules for electric field lines. An electric field line is just a really good tool to describe an electric field without having to do a bunch of numbers. We also call these lines of force because it turns out they are actually force lines. Now, when the field line is strong, these are going to be very close together. Here's my field test analyzer. Basically, I'm going to count the number of field lines in any given field. Now look at this. Right there, we have 1, 2, 3, 4 field lines. Clearly, that is a stronger field than out here where I have 1, 2 field lines. So where the field is strongest is where they are closer together. Okay, and where the field is weakest, they're further apart. See, the field is actually fairly weak out here, but it's stronger in here. What about here? It's actually it's almost uniform here, but it changes as you go out. See, we can go from 3 down to 1. This is really cool. Here's a lightning rod. Look at this. Isn't this cool? Where's the electric field really strong on a lightning rod? It's up toward the peak. We'll discuss why in a bit. Now, there are rules. This is physics. There are always rules. Okay. Electric field lines start on positive. So if you have a positive charge, they're always going to go out. Start on positive, end on negative. Okay, they always end on a negative charge. And that's not a very straight line there. Now, the number of lines drawn, entering or leaving, is proportional to the magnitude of the charge. So if I have a 1Q charge and say I give it 4 field lines, 1, 2, 3, 4, I'm not very imaginative. And then I have a 2Q. I'm going to need to have how many? If it's twice as much charge, and I had 4 to start with, I'm going to need 2, 4, 6, 8. I'm going to need 8 lines. So 1, 2, 3, 4, 5, 6, 7, 8. And I apologize, my pen is being strange today. So this is what 2Q would look like if you drew 1Q this way. Now, field lines cannot cross. I won't get into all the physics behind this, but it's kind of a cool concept. Just make sure they never loop around. If I were to give you this right here and some strange configuration, and we did this right here, and this is my field lines, that could not occur. Field lines don't cross. Now, an electric dipole is something you need to know about. Di means two. Pole means extremes. So a dipole is when you have two equal but opposite charges. Okay, positive and negative charges. So here's an example. This is plus Q and minus Q. It starts on positive Q and goes off to negative Q. But do you see that, what those field lines look like? I want you to think about what you have seen back in 7th grade or IPC. What does that look like? We're going to address what that looks like later. Now, the direction of the electric field itself is tangent at any particular point. So let's say at this point right here, it goes off this way. Well, let me switch to pen. I thought I had. At this point right here, tangent is actually straight off. Right here, the electric field goes that way, and right here, down. Let's do it right here. Okay. So, what do you do if you have two equal positive charges? Well, it winds up, it's being repulsed. So it starts on positive and it curves away. It starts on positive and curves away. And it does this for both charges. So you see, you wind up with this point right here. We actually wind up with 0 electric field. You can see it demonstrated right down here. Isn't that just really cool? Do you see how they become almost completely parallel? Where here on this dipole, they actually become almost straight. And actually, they do become almost straight and parallel. More lines you draw per charge, the more you get the sense of this field. Clearly, if I had simply done 4 lines, okay, and when you do this in class, this is important, do enough lines to make it reasonable. Golly, my pen's not wanting to work in that spot. Sorry. Don't know why it's doing that. So I've got one going up this way. I mean, you could do it this way, but that's 6 lines, I guess. Don't know why that's not working. There it goes. That doesn't describe much. Do you see how much more detailed this is? Now, what if you have unlike charges? All right. Well, then the number of charges, say you have negative q and plus 2q. All right. For the lowest number one, I have 1, 2, 3, 4, 5, 6 lines going in. So I'm going to need, of course, 12 lines going into the plus 2q. And some of these lines will simply come from kind of out of nowhere, really. Now this, they're actually drawing equal potential lines, but you can, on top of the electric field lines. Now, isn't that just really cool? You don't have to be able to draw that, but it's just cool. Now, remember when we discussed lightning rods? What do you do if you have a conductor with a pointy end, like a lightning rod? It turns out that there is more charge gathered at the point, and so you have a stronger electric field. Because you have a stronger electric field, more, if you have a cloud here with a bunch of negative charges, they're going to be more strongly attracted. And so you wind up with the lightning hitting your lightning rod or your pointy-ended conductor rather than the building with all of the people in it. Okay, and this truly is my drawing, so my students, I apologize. Electric fields are fascinating.